Adam. I'm an associate professor at WSU and associate director of the State of Washington Water Research Center. And I'll be talking about BioEarth. And Roy mentioned that BioEarth is funded under the USDA Earth System Modeling Program. And I do want to mention, though, that a lot of what we're doing with BioEarth is based off of work that we're doing with other projects. So we have quite a bit of funding through the Washington State Department of Ecology, Office of Columbia Research, to build a lot of what we're doing. And if some of you have heard of AirPact, the air quality forecast system, a lot of it is based off of that. And we have funding through NSF IGERT for nitrogen cycling. So it's a large team of collaborators. Today, because of the focus on the interactions between land use, natural resources management, climate, and water, I'm not going to be talking about everything that the team is doing, more focused in on agricultural management in cropping, forest, and rangeland systems and what we're doing there. But we do have a large group of people who are working on the nitrogen cycling, looking at sources, atmospheric transport of nitrogen, fates, and impacts on ecological systems. So that's a big part of what BioEarth is that I'm not really getting into today. The motivation for what we're doing is, and I think we've heard this entire conference, so this is nothing new, but that we need to, sorry, I got a little bit of a cold here, that actors are needing to make resource management decisions in the face of global change, and they're confronted with numerous uncertainties around those changes in very complex systems. So it's the complex systems here that we're trying to really deal with head-on through integrated modeling. Climate science information is underutilized for decision making, and there's a need to close the gap between science information deemed usable by scientists and those by non-academic actors. So the objectives of this talk: I want to discuss movement of our integrated modeling projects or Earth system modeling projects along a continuum from generating not only scientific information, which is also very much what we're doing, but also being able to generate information that can be used for management decisions, either natural resources or agricultural resource management decisions, using BioEarth as an example, but also recognizing that there's a lot of other projects out there that are doing this. And so one of which is the PRIMA project out of PNNL. They're doing this, focused a little bit more on the energy and water interactions. We're focused more on water and agricultural interactions. So integrated modeling, basically the definition is that you're taking models developed solely within their academic disciplines and learning how to interact. And so these can be either really tight interactions where you're embedding the code within and they're communicating regularly, or loose interactions. But the advantage is that we can start to look at these complex systems. You can see how these different systems are reacting and feeding back to affect each other. And so you can start revealing changes in policy or best management practices and start uncovering unintended consequences that you couldn't foresee without looking at how that affects the other sectors. So basically looking at the Earth as a system. So our goals for BioEarth are to improve the understanding of the interactions between coupled carbon, nitrogen, and water dynamics and human actions at the regional and decadal scales within the context of global change. So we are trying to better understand, this is sort of our scientific question, but understand the role that resource management activities have in impacting Earth system dynamics. But then we also want to be able to inform sustainable resource management decisions. And so what we're trying to do is provide a broader context, uncovering things like unintended consequences of changes in policy or management practices. So with the goal of aiming to provide for human needs while reducing our impacts on the environment. And so a lot of this is actually in an overview paper that we published earlier this year. So that's in climatic change. So this provides an outline of what I'm talking about today. What we're trying to do with the Earth system model is move it along to this continuum. I mentioned that earlier, but what do we need to do to make sure that we can use this information for informing management decisions? So this is not inclusive at all. This is not comprehensive. This is just some of the things that we're dealing with head on at the moment. For one thing, it needs to be regionally specific. And we heard earlier, I think from John Abatsoglu, talking about the need to do that for atmospheric dynamics purposes, but we also need to do that in terms of looking at the impacts of changes in the atmosphere, because we need to be able to incorporate into our model processes that are really only relevant in some ways at that scale, over the regional scale. So one of which is the water law, or the water and the natural resources management context. So looking at water law and overlaying that, which is really hard to do if you're looking at global scale, but easier to do at the regional scale. We also need to be able to capture these decision-making processes explicitly. And so I mentioned PRIMA. I'm quoting, their overview paper there, and that they're also working on that as well. Looking at resolution, there's been a call lately for doing hyper-resolution studies over larger scales. And so we need to really think hard about what scales these processes occur over and make sure that we're capturing those scales that are dominating the processes that we're interested in and the interactions between them. And then we need to involve stakeholders on our team. Okay, so this is the Columbia River Basin. I don't think I need to spend too much time on this except to mention that it does have a lot of forest resources. Rangeland resources are shown there in yellow, and then agricultural landscapes. It spans the entire Pacific Northwest region and going up into BC. And you can see overlaying here are the Yakima River Basin, Spokane, Salmon, and Willamette are all housed within that. A lot of changes. You've heard about how the climate's projected to change here. There's a lot of multiple competing in and out of stream water uses here. Irrigation is the largest consumptive use of water in the area. There's a treaty that's under negotiation, under review at the moment, and we have a lot of intensifying issues here. So because of all of the unique things that we have in the Columbia River Basin, again, we need to be able to incorporate regionally specific processes and information. So there's a real need, again, to focus on the regional scale. And I think that this is something that's being more and more acknowledged among Earth system modeling communities. So this is the BioEarth framework. This is the top-level BioEarth framework without all the acronyms, where we have the whole entire thing driven by global climate, but we also are capturing meteorological processes through WRF, atmospheric chemistry through CMAC. We have two different land surface models that we're working with and developing simultaneously. This is a very modular framework, and so the idea is that while we're working on these models, we use one sometimes, other times. So we're using an adaptation of the VIC model for the land surface for our cropping systems, and then for our rangeland and forest systems, the RESIS model, we're upscaling. I'll talk about more of that in a minute. We also have stream flow routing and reservoir operations, and we're looking at nitrogen export from the rivers. And we have right in the middle there, we have an economics piece, and the lead of our economics team is going to be talking next here. So again, we're trying to explicitly include decision-making practices, and the three agricultural sectors we're looking at are croplands, rangelands, and forests. But then we're also looking to see how those interact with water supply, water quality, air quality, and then being able to look at exogenous agents like changes in policy. Okay, so those are the types of decisions we're in, and incorporating each and every one of those is actually quite a bit of work. I'll talk about more of that in a moment. So as we investigate, for example, crop selection, we can look at impacts depending on which parts of this model we're running. We can look at a variety of impacts: air quality, water quantity, changes in terrestrial ecosystem health, and then economic impacts. Okay, so one of the biggest developments that we've done that has attracted quite a bit of interest is a coupling between the VIC model, which you've probably heard a lot about at this conference. It's a large-scale hydrologic model, and then a cropping model developed out of Washington State University around the same time frame. So we have a direct coupling between these two models with CropSys. Basically, we've ripped out all of the hydrology, and it's acting as a dynamic vegetation model that's sitting within VIC for cropland systems only. And so VIC is handling all of the hydrology. CropSys does all of the crop growth and phenology, the nitrogen cycling, the carbon cycling, and it's also, we're able to simulate the important agricultural management practices of interest. So this is work that is going to be published soon by one of my PhD students, Kayvon Malik. As part of our forecast projects with the Washington State Department of Ecology, we take VIC CropSys. We have a reservoir mollicalsum that we've adapted for water rights curtailment processes. So we've overlaid water rights information in there, and we can look in in-stream flow rules, and we can look to see under projections or drought situations, what the impacts then would be in terms of curtailment of water rights to irrigators, and what the crop yield impacts would be from that. And we've linked that with our economic modeling work, looking at agricultural producer response. So two of the things, on the long run, we're looking at how the crop acreage would adjust. And then on the shorter run, in times of drought, how can the irrigators selectively deficit irrigate, meaning they're not providing the full amount of water to specific crops. Okay, I'll talk about more of that in a minute. And so we can provide, we can run it with different future climate scenarios, different water management scenarios, different economic scenarios for trade, for example, and look at impacts on water supply, irrigation water demand, and then the deficit, and then the impacts of that deficit as well. So this is a student of mine as well, Kirti Rajagopalan, who's publishing this paper. We're about ready to submit it, looking at changes in the crop yield for different types of crops. And the changes can be either fully positive across the area. This is just Washington of what I'm showing. Or they can be negative in the case of corn, or a mix of positive and negative results in the case of spring wheat. But she's really interested in teasing out what factors are controlling those responses. And so this is really the heart of her dissertation, is to try to understand to what extent, and for each crop, and whether or not it's irrigated or non-irrigated, are these changes being driven by precipitation, by temperature, by combination of precipitation, temperature, how much is driven by changes in CO2, and then we have some changes from our economic modeling team and looking at the change in crop mix into the future. And so this is quite different at whether or not you look at dryland crops versus irrigated crops. The dryland crops primarily a positive response, because the increase in CO2 does make them more water use efficient as well as energy efficient. And so because they're already generally water limited, that increase in water use efficiency will cause a dramatic increase in their yield. Temperature effects are largely reducing the yield because the crops do go through their phenological stages faster and don't have enough time to gain biomass through that time. So we're looking at an array of both positive and negative impacts, and going into this is for a 20-year forecast, but what she's really interested is looking at how those factors play out moving beyond 20 years. So if the CO2 fertilization effect for C3 crops is primarily to increase the yield, and temperature primarily causes a reduction in the yield, in 20 years from now we're looking at mostly the CO2 effect having a positive net response and outweighing the warming response. But at some point in time, when does that turn around, and the warming effect will dominate that? So are we looking at a shorter term? If we only look at 20 years planning horizons for crop productivity, are we looking at a pretty rosy picture, followed by at some point in time in the yields really going down or crashing below that? So she's interested in that kind of a question, but she's also looking at how can plant variety and planting date allow the farmers to adapt to these changes. I have a PhD student, Kayvon, again, who's looking at irrigation management and he's done quite a bit of work to incorporate irrigation technology management specific decisions into the model, taking a very good look at the different losses, both in terms of runoff and energy from irrigation management. And he's looking at adaptation through irrigation management at shorter time scales, or irrigation technology at longer time scales. We have an economic student working with Mike Brady, looking at basically using our crop response curves that we're getting from CropSyst. So we have crop yield on the y-axis and the amount of water input on the x-axis, and looking at deficit irrigation, where in a time of curtailment or water rights restrictions, can they not apply as much water? So we have, if you moving on that arrow from the right to the left, we have a larger savings in water without much of an impact in terms of yield. So she's going to be doing some economic analysis, looking at strategies for doing deficit irrigation in our agriculture, mostly focused in the Yakima River Basin. Okay, so that's our cropping systems. We're doing quite a bit of work to incorporate decisions for rangeland and forest ecosystems too, using the rhesus model, which is developed out of Santa Barbara with Naomi Teague. and she's a team player on BioEarth. And so the RHESUS model is a catchment scale model. So I mentioned earlier about hyper-resolution studies. So what we're doing is we're taking this catchment scale model. It has carbon and nitrogen cycling coupled with dynamic vegetation and both vertical and lateral hydrology. Most of the large-scale models that you're used to seeing, like VIC or CLM, do not have lateral flow hydrology at all. They're column models. They only have vertical information. And so the lateral drainage does actually impact dynamic vegetation and nitrogen cycling. So it's actually a very important piece of what we're trying to do here. So we're trying to take this different paradigm of models and has never really been implemented at regional scales, and we're developing it for rangeland and forest, and then trying to learn how to develop it at the regional scale. And RHESUS was a really great choice for us because it is so much used by many by scientists who work at the catchment scale, who work with managers, who work with field researchers with CZOs or the LTERs or NEON sites. So it's constantly improving. So all of the improvement that RHESUS is constantly undergoing is becoming constantly going to be incorporated into BioEarth. Okay, and so our team down in Santa Barbara has looked at the impacts of forest thinning on water supply, for example. And this is in the Santa Fe municipal watershed, so outside of our domain. But looking at, to the extent that thinning can offset projected changes in water availability. Okay, showing that thinning at 30% on the one hand does offset reductions in annual stream flow, but the timing of the stream flow shifts to earlier in the year. So that's not, so it's kind of a trade-off there. So that's one of the powerful aspects of RHESUS. It is primarily a forest model. We're doing work to develop it for rangeland, and it has a long history for we're looking at questions like this. Okay, so I have another student, Julian Reyes, who's looking at rangeland systems, and so he's been doing quite a bit of work to develop RHESUS to be able to better handle grasslands. And so he's looking at there it is. He's looking at the interactions between humans, so basically management in terms of grazing intensity and grazing methods, changes in spatial temporal methods, and climate, and the impacts of these management changes on nitrogen emissions to the atmosphere, nitrogen leaching to the ground, and methane emissions. So again, I want to talk about the hyper-resolution aspect. There is a call out there to do hyper-resolution studies. So the RHESUS approach, this is a catchment scale model. It also runs on polygons, or what we call patches. They're not regular grid cells, and they're very fine. Usually the lowest resolution is around 90 meters size. And so they're spatially explicit, where we have lateral connectivity. We can actually redistribute soil moisture down the hill slope and see how that interacts with the nitrogen cycle, the carbon cycle, and with dynamic vegetation. Okay, and the VIC approaches, this is VIC and CLM and other models like that, are column models where we don't have lateral connectivity. Okay, so we're trying to bridge these two paradigms, and we're doing this through Kepler's workflows, where we can actually launch watersheds across the whole basin at hyper resolution, at very fine resolution, and then invoke changes on that and look at how it responds. But to do that, that's very extremely computationally intense to be able to run hyper-resolution studies at the regional scale. So what we're trying to do is bridge the paradigm. So bridge these two paradigms of model through having larger patches that incorporate statistical subgrid variability in the way that VIC does, okay? So we have much larger patches. It's sort of moderate resolution patches between these two models, and within that we can capture the heterogeneity due to land cover, for example. And this does increase, it decreases our simulation time, but depending on the biome that we're looking at, the performance is not that much reduced, okay? But this begs the question, at what scale do we run these at? Do we need to keep the finest resolution? Can we go with the larger resolution? And how much of that statistical subgrid variability and land cover do we need to represent? So we have a lot of work that we're doing in terms of understanding what types of heterogeneities and at what scales must we represent to adequately capture large-scale aggregate land surface response to a climate change or a change in management. So we're really interested in the large-scale aggregate response, the regional scale, the watershed scale response, to what extent is that response being driven by heterogeneity at the very fine scale? Okay, so does fine scale parameter heterogeneity matter? So one of the things we're looking at is across biomes and for metrics of interest, like net primary productivity or nitrate leaching, is fine scale land surface response to an invoked change nonlinear. And so this question comes out of population ecology, where using scale transition theory, where the theory says that at fine resolution, if the response is linear, then you can aggregate and have larger patches and still represent the aggregate response. Okay, but if it's nonlinear, then you cannot aggregate that patch, make a larger patch, and still capture the reasonable response. Okay, so by taking the model, running it at the finest resolution, and then invoking change and looking to see if it's nonlinear, we can start to come up with a recommendation on whether or not we need to run at really fine patches or we can go ahead and upscale. Okay, if it is nonlinear, then the next question is, why does it matter? Is it because, so what type of heterogeneity is driving this response? Is it because there's a large heterogeneity in land cover or soil characteristics? Or is it because we need to be able to capture basically soil redistribution down gradient, down the hill slope, in ways that the larger scale models just can't do? Okay, and then after we ask these questions, how can we use this information to inform how we're doing the rhesus upscaling? So just a couple of examples on this. This is the HGA Andrews site in Oregon, and for a nitrogen cycling question, where we've invoked rather unrealistic increases in nitrogen deposition on the x-axis here. Yep, so on the x-axis here, this gets into very unrealistic increases in nitrogen deposition, and then looking to see how the nitrogen cycles responds in terms of organic soil nitrogen, mineral soil nitrogen, plant biomass, stream flow nitrates, and stream flow dissolved organic nitrogen. And in the perturbations that are within realistic ranges, it is a highly linear response. Okay, so here we can argue that for this particular metric of interest, we can go with a larger patch size. As you get into unrealistic increases in nitrogen deposition, it does become nonlinear. However, if we look at changes in temperature, throughout temperature changes up to 5 degrees Celsius, again, the responses are linear, so we can upscale. This is work from Julian Reyes, looking at rangelands. This is in Kansas. And so basically what he's doing is also invoking a change in temperature in the grassland system and looking at the change in leaf carbon, root carbon, soil carbon, and net primary productivity and finding a very nonlinear response. So in this case, the system, probably because of being more of a drier landscape, is nonlinear. We need to run finer resolution patches. So then the next question after this is we start looking at why that matters. Okay, so I'm not going to show you any of the results for looking at whether or not it's due to heterogeneity in parameters or soil moisture redistribution. You know, I always put this slide last not because it's the least important part of what we're doing, but because I really want to make sure people remember what we're doing. So if you put something last, they'll probably remember it longer, right? So one of the most important parts of what we're doing is working with stakeholders early on in the project and throughout the process, trying to understand the factors that drive resource management decisions and information needs of the decision makers, how they prioritize their various concerns, and what they want to know about the future. Okay, and we actually use this information. We've done a lot in terms of informing model development. We've made very strategic changes in our model development plans because of these workshops. Also informing our model scenarios and communicating and vetting results. So we've had, I think, 5 different workshops on nitrogen, water supply, air quality, forest, and rangeland. We have one coming up on water quality, and we're continuing communication. And so this is Liz Allen's work with Chad Kruger in the Center for Sustaining Ag, who's doing this work here. So overall, integrated modeling frameworks can and should be used for informing policy and management decisions, highlighting trade-offs, feedbacks, and thresholds, and uncovering unintended consequences. There are numerous opportunities to increase the usability of these frameworks through being specific at the regional scale, incorporating information that we can only incorporate regionally. And you know, I keep hammering this point because I do give this presentation to basically the NCAR, or system modeling crowd, and they do not incorporate any additional processes into their land surface model if it cannot be implemented at global scale. So this is what really makes BioEarth unique, is that we are focusing on one region, so we can do that. Explicit inclusion of decision processes, representation of spatial heterogeneity, and really thinking carefully about not just, oh, let's make it as fine resolution as we can, you know, and meet this call of hyper-resolution, but thinking carefully about what that means and only make it in fine resolution when we have to, so that we can actually get the correct response at the aggregate scale. And then including stakeholders as team members. So the sign says stop, so I will stop and see if you have any questions.
Hi, my name is David Diaz. I'm with EcoTrust. I'm curious about the management actions or decision makers that you're expecting to use the outputs of this, and kind of what that process looks like of how a farmer or forest owner would use this information. It sounds like you're still talking at a fairly larger scale than a private private landowner would be operating on. So is this something that like an extension forester or extension agent, would communicate that in this county, this is the type of practices that we look at, or is it something that you're expecting individual landowners to be able to engage with this information?
Well, I mean, we're still trying to figure out what exactly they're looking for in terms of what kinds of products we need to put out there. But I really like, Chad Kruger was up there, some words that he uses, what we're trying to do is provide the broader context. So these are his words, of a decision that we're trying to inform. And so I don't think you would ever use this information in isolation of more specific tools, decision support tools, but it's providing a broader context of what are we missing when we change a management action, or there's a change in policy and responding to that, that is completely neglected when you have really decision-specific support tools. So it's providing a broader context, uncovering things like, there's downstream feedbacks and changing water, in improving your water conservation practices that impact downstream irrigators, for example, or there's impacts to the atmosphere that we neglected that impact other sectors. But so that's one thing. I might actually have. Probably won't punt, but we are actually trying to figure out more if there's more specific ways we can provide this information to the stakeholders themselves. Paul, did you want to ask a question?
I'll throw one more in. I'm just curious about your choice of. If you really want me louder. I'm curious about your choice of water quality parameters. So you just focusing on nitrogen. For example, phosphorus and sediment have really significant environmental impacts. So I'm wondering why those aren't included.
Yeah, no, thank you for asking that question. Water quality is actually not the focus of this particular project. We're really looking at more water resources, quantity, and then land-atmosphere interactions in terms of the nitrogen and carbon cycles. We do include nitrogen as more of an export. We're not doing any kind of fine-scale physically based modeling of the water quality, and it is focused on nitrogen. However, you're going to hear from Mike Brady in a moment. Wisdom is a companion project to BioEarth, where there is more of a water quality focus, although I don't think he's talking about that today. But just know that this is a companion project. We're trying to do a better job with water quality, so we haven't really so phosphorus and sediment, you're right, is not part of BioEarth, although in the plans I do hope to get that incorporated at some point.